Sketch the graph of the function f of x equals 2 plus 3x minus x cubed by determining the parts a through I. F of x equals 2 plus 3x minus x cubed, which is a polynomial. So for part A, the domain will be all real numbers, or negative infinity to positive infinity. For part B, we want to determine whether there's any symmetry or not. This is done by evaluating f of negative x and comparing it to the original function f of x. F of x is made up of two odd powers. This is a power of 1 here implied, that are subtracting with each other. However, there's also a constant, which is an even power, and therefore f of x will not have any symmetry. But f of negative x will be 2 plus 3 times negative x minus negative x cubed, which is 2, a 3 times a negative x is negative 3x. A negative x cubed is negative times the negative will be positive, and then x cubed. Comparing this to the original function, the first term is the same sign, so this does not equal the negative of the original function, and it will not have origin or odd symmetry. Comparing the next two terms to the original, they are both opposite sign of the original. So this also does not equal the original function f of x, so it will not have y-axis or even symmetry either. So for symmetry, it has none. For part C, we want to determine the y-intercept. This is the point that the graph crosses the y-axis at, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate 0 back to the original function. So y equals f of 0, which is 2 plus 3 times 0 minus 0 cubed. 3 times 0 is 0, minus 0 cubed is 0. 2 plus 0 minus 0 is 2. We have an x-coordinate of 0, and we have a corresponding y-coordinate of 2. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. Y is f of x. We're going to set it equal to 0 and solve for all x's. We will want the function to be fully factored for this. So back up here, we are going to factor this function. We can break apart the plus 3x into plus 2x and plus 1x. The reason for doing that is we can now pair off and try group factoring. There's a common factor of 2 with the first group, leaving a 1 plus x after we factor the 2 out. There's a common factor of x, leaving a 1 minus x squared after we factor the x out. 1 minus x squared factors further, since it's a difference of squares, into 1 plus x and 1 minus x. Since we have matching factors of 1 plus x here and here, group factoring is possible because that 1 plus x can factor out of the entire thing. And that will leave a 2 plus an x times a 1 minus x. So this is going to be 1 plus x multiplied with, there's a 2, and we're going to distribute the x in here. It'll be plus x minus x squared. It's probably best to factor a negative out of there because that is a trinomial quadratic and we will want the x squared term to be positive. The negative will move to the very front of everything. And now it'll be x squared minus x and minus 2. I put it in descending order and changed the signs on everything after factoring the negative out, which can further factor into x and x. We need two numbers that multiply to be a negative 2 and add to be a negative 1. Negative 2 and positive 1 will take care of that. One more thing we can do here, 1 plus x and x plus 1 are the same thing, so we can write them both as x plus 1, but they're multiplying each other, so we can combine them together and call it x plus 1 quantity squared. There's also the x minus 2. So there's the fully factored version of the function. 0 equals to negative x plus 1 squared times x minus 2. Since y is f of x, we're setting it equal to 0. We're going to solve for all x's here. It's already factored, so this tells us that x equals negative 1 and x equals positive 2. The corresponding x coordinates to go with the y coordinate of 0. So we have a negative 1 comma 0 and we have a 2 comma 0. For part E, we want to find any vertical asymptotes. F of x is a polynomial with no denominator, so there will be none. For part F, we want to find any holes. F of x does not have a denominator, so there will be none. For part G, we want to determine any end behavior, horizontal asymptotes, or slant asymptotes. Since f of x has no denominator, it will not have horizontal asymptotes or slant asymptotes. But since it is a polynomial, it will have positive or negative infinity end behaviors. We can determine the left end behavior by taking the limit as x approaches negative infinity of f of x, 2 plus 3x minus x cubed. Only the highest power term will matter here. That's this one. Negative cubed is negative times a negative is positive, and then infinity cubed is infinity. So this will work out to positive infinity for left end behavior. Right end behavior can be determined by taking the limit as x approaches positive infinity of the original function. Only the highest power term matters here. Positive infinity cubed is positive infinity times the negative will be negative infinity. For part H, we want to determine intervals of trend, relative maxima, relative minima, plateaus or cliffs. All of this involves the first derivative, f prime of x. The derivative of f of x will be 3 minus 3x squared. We will want to fully factor the first derivative. There's a common factor of 3. Factoring that out, we'll leave behind 1 minus x squared, which is a difference of squares and can factor further into 1 plus x and 1 minus x. We can now set the numerator equal to 0 and the denominator, if there is one, also equal to 0 and solve for all x's. This will lead to x equals negative 1 and x equals positive 1. We will check to see which of these are in the domain. They're both in the domain. They are both, therefore, a critical number. We can now draw a domain line, a line representing the domain. It has no left end because it starts at negative infinity. It has no right end because it ends at positive infinity. We can put any critical numbers in order on the domain line. Negative 1 comes first. and then positive 1, which splits the domain interval up into 3 separate intervals. We can test the trend in each of these intervals by picking a test value in each of them. The first interval, negative infinity to negative 1, contains negative 10. The next interval, negative 1 to positive 1, contains 0. And the next interval, positive 1 to positive infinity, contains 10. We can then test the trend by plugging these test values into the first derivative. We only care whether it is positive or negative, so we're going to plug into the fully factored version. That's this one here. Starting with negative 10, 1 plus negative 10 is a negative. 1 minus a negative 10 is a positive. Negative times positive is a negative. Times that positive 3 will still be negative. We have a negative first derivative in this interval, which corresponds to a decreasing trend. Plugging 0 into the fully factored version of the derivative, 1 plus 0 is positive. 1 minus 0 is positive. Positive times positive is positive. Times that positive 3 will still be positive. We have a positive first derivative, which corresponds to an increasing trend. Plugging positive 10 in, 1 plus 10 is positive, 1 minus 10 is negative, positive times negative is negative, times that positive 3 is still negative. We have a negative first derivative. This corresponds to a decreasing trend. Right at the critical number of x equals negative 1, we have a trend change from decreasing to increasing. That makes x equals negative 1 be a relative minimum. It has an x-coordinate of negative 1, and it will have a corresponding y-coordinate, which can be found by plugging the x-coordinate back into the original function. So y equals f of negative 1, which is 2 plus 3 times negative 1 minus negative 1 cubed, which is 2. 3 times a negative 1 is a negative 3. And negative cubed is negative times the negative will be positive. 1 cubed is 1. 2 minus 3 is negative 1 plus 1 is 0. We have a corresponding y-coordinate of 0. Right at the critical number of x equals positive 1, we have the trend change from increasing to decreasing. That will make x equals 1 be a relative maximum. It has an x-coordinate of 1 and a corresponding y-coordinate, which can be found by plugging the x-coordinate back into the original function. So y equals f of 1, which is 2 plus 3 times 1 minus 1 cubed, which is 2. 3 times a positive 1 is a positive 3, and then minus 1 cubed is a 1. 2 plus 3 is 5, minus 1 is 4. It has a corresponding y-coordinate of 4. For part I, we want to determine the intervals of concavity and any inflection points. This all requires the second derivative, which will be a negative 6x. We can now set the numerator equal to 0 and the denominator, if there is one, also equal to 0 and solve for all x's. We have to divide both sides by negative 6 here. Gives x equals 0. We'll now check to see if this is in the domain. The domain is all real numbers. 0 is a real number, so it's in the domain, and that makes it be a candidate number. We can once again draw the domain line. It has no left end or right end. Since it begins at negative infinity, goes to positive infinity. We can put all candidate numbers on here. X equals 0 is the only one. This splits the domain interval into 2 separate intervals. We can pick a test value in each of these intervals to test the concavity. In the interval negative infinity to 0, negative 10 will be in there. In the interval 0 to positive infinity, positive 10 will be in there. We can test the concavity by plugging the test values into the second derivative. We only care whether it is positive or negative. Plugging a negative 10 in here will give us a negative times a negative, which is a positive second derivative. This corresponds to concave up. Plugging a positive 10 test value in here, negative times positive is negative. We have a negative second derivative. This corresponds to concave down. Right at the candidate number of x equals 0, we have the concavity changing from concave up to concave down. That means x equals 0 will be an inflection point. It has an x-coordinate of 0. It has a y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 0, which is 2 plus 3 times 0 minus 0 cubed, which is 2. 3 times 0 is 0, minus 0 cubed, which is 0. 2 plus 0 minus 0 is a 2. It has a corresponding y-coordinate of 2. We can now draw the graph. We have a vertical axis and a horizontal axis. The domain is all real numbers, so it will cover the entire span of x values. It was found to have no symmetry. It does have a y-intercept of 0, 2. So that'll be right here. And it has x-intercepts of -1, 0 and 2, 0. -1, 0 will be here. 2, 0 will be here. We'll want to label each of these. So we have, this one is -1, 0. We have this one as 2, 0. And we have this one as 0, 2. We have left end behavior that will be positive infinity. That means it'll go up here on the left end. And right end behavior of negative infinity. That means it'll go down here on the right end. We'll be sure the graph follows that. We have a relative minimum at -1, 0. So right at -1, 0, we can give it a relative minimum type look. It'll look something like that. Right at 1, 4, it'll have a relative maximum. So that will be up here. So we'll give it a relative maximum kind of look, and let's label that as 1, 4. And then right at 0, 2 will be the inflection point. It's supposed to be concave up to the left side of that. So we'll give it a concave up look. That means it's curving upward. So it'll be like that. And then to the right side of it, it should be concave down. So we can connect this together. And it's supposed to go through this intercept here with a concave down type of shape to it. And it does have the left end and right end behaviors as expected. This then will be the graph of f of x.